In our last video, we defined the directional derivative. The derivative of f in the direction of a vector u, which needs to be a unit vector, at p naught, is the limit as delta s approaches 0 of x naught plus delta s times u1, where u1 is the I component of vector u, unit vector u, comma y naught plus delta s u2, where u2 is the j component of vector u, minus f of x naught, comma y naught. And the whole idea is that we're moving from some point in the plane in the direction of some s axis. And we even went as far as to parameterize that s axis. And this time when I write down the parametric equations of this line s, I'm going to let the parameter be called s. And I know whatever value I plug in for s is the distance I've moved. So I could think about plugging in delta s here to get from the point x naught, y naught to that point. But what I realize I have now is the situation where I start with an s. These two equations take me from an s to an x. And then my function finally turns that into a f of xy, or a z. And so here, I have the definition of a directional derivative, but I also have a dependency diagram, and I should be able to write a chain rule for df ds. Well, I would have a partial with respect to a partial of f with respect to x, and a partial of f with respect to y, dx, ds, and dy, ds. All right, well, partial with respect to x times dx, ds. But dx, ds is linear, right? When I take the derivative of this with respect to s, I just get back u1 plus the partial of f with respect to y times, well, again, dy, ds. Take the derivative of y naught plus u2s, I would just get u2. And so here's my chain rule for df ds. The partial of f with respect to x times u1 plus the partial of f with respect to y, u2. And looking at that, u1 and u2 are components of a vector. Partial of f, partial of x times. This is a dot product between a vector made up of my partial derivatives, and I'd be evaluating my partial derivatives here at a particular point, and that unit vector u1, u2. Well, partial derivatives are usually pretty easy to calculate. I'm given this vector. This is a much nicer calculation formula. So if I was to write out all the details, df ds is also equal to my partial with respect to x evaluated at the point p naught, my partial with respect to y evaluated at that point p naught, dot u1, u2. So let's think about the example we did by using the definition in the last video. F of x comma y was x squared minus y squared. We started with the vector v being the vector 1 minus 1. And we were moving away from the point 1 comma 2. So let's see what happens if we calculate our directional derivative using this new idea. So I need to know my two partials. Well, fx is 2x and fy is minus 2y. I need to evaluate those at the point, well, that should be p naught if I'm matching all of my notation from previously. Well, these are pretty easy to evaluate. This only depends on x. I get 2, and fy of 1 comma 2 would be minus 4. So the directional derivative, according to that chain rule, moving in the direction of u away from point p naught should be the vector 2 comma minus 4, dot the unit vector we calculated, which was 1 over root 2 comma minus 1 over root 2. And if I was going to point out something that's the number one thing a Calc 3 student misses, it's forgetting that this is a unit vector. All right, so I have 2 over root 2, which is just root 2, plus minus and a minus. All right, so 4 over root 2, 6 over root 2, which is 3 root 2. Exactly what we got before. This formula seems to work.